Hey, welcome. Today we are diving deep into a single molecule that could completely reshape global trade as we know it, ammonia. You've probably heard the buzz. It's being talked about as the zero-carbon fuel that might just power the future of the shipping industry. So what's the real story? Let's get into it.
Okay, so before we can even think about powering the world's massive cargo fleets with ammonia, we've got to ask a really fundamental question. How do we actually make this stuff? And for anyone trying to navigate the future of shipping, the answer to this is absolutely critical.
You know, the recipe for making industrial-scale ammonia is this century-old marvel called the Haber-Bosch process. But like any good recipe, it doesn't work unless you have the right ingredients. And the most important and, frankly, the most challenging one to get is hydrogen. So let's start there. How do we get our hands on all the hydrogen we need?
Right, our first stop on this journey is the most common method out there for making hydrogen at scale. It's a process known as steam methane reforming, or just SMR for short. You can really think of this as the engine room that powers the vast majority of the world's entire hydrogen supply today.
So what exactly is SMR? Well, at its heart, it's a high-temperature chemical reaction. You take natural gas, which is mostly methane, and you blast it with superheated steam. This reaction literally rips the molecules apart and creates hydrogen. Now, it's pretty energy intensive for sure, but it's a technology that's been around forever and is used all over the world.
So the whole process happens in a few key steps. First, you react the methane and steam over a really hot nickel catalyst. Then, you often add air, which not only provides more heat, but, and this is super important, it also gives us the nitrogen that we're going to need later. After a couple more refining steps to get even more hydrogen and clean everything up, you're left with our key ingredient, super high-purity hydrogen.
If you want to boil this entire complex industrial process down to a single line, this is it. You put in methane and water, and you get out hydrogen. But, and this is a huge but, look at that other thing that comes out, CO2, carbon dioxide. That little detail is a crucial part of the story, and we're definitely going to come back to it.
Okay, so now we've got our hydrogen from the SMR process, and we've got our nitrogen from the air. We are finally ready to combine them to make ammonia, using a process that literally changed the world. And look, I am not exaggerating how important this is. The scientist Vaclav Smil once said, the Haber-Bosch process is arguably the most important invention of the 20th century. And why would he say that? Because this process is what allowed us to create cheap fertilizer on a massive scale, which has fed billions of people. And now, that very same process might be the key to fueling our ships. But here's the catch. The process has this core challenge. You can think of it as an engineer's dilemma. To get the reaction to happen fast, you need really high temperatures. But the high temperatures actually mean you get less ammonia out of each pass. On the flip side, lower temperatures would give you more ammonia, but the reaction would be painfully slow. The absolute genius of the Haber-Bosch process is finding that perfect sweet spot right in the middle. So here's how they cracked it in a nutshell. First, you take your hydrogen and nitrogen and mix them in a super precise 3-to-1 ratio. Then you have to purify the gas, because the iron catalyst they use is really sensitive. After that, you compress it to absolutely immense pressures. We're talking 150 to 300 times normal atmospheric pressure. You heat it up over that catalyst, and boom, you get ammonia. The final gas mixture then cooled down, and the ammonia turns into a liquid, which makes it really easy to separate out. Now, after that first pass through the reactor, only about 10 or 20% of the gas has actually turned into ammonia. And you might be thinking, that doesn't sound very efficient. But here's the brilliant part. The unreacted hydrogen and nitrogen, they aren't just thrown away. They are captured and looped right back to the beginning of the process. This recycling loop pushes the overall efficiency of the whole system to an incredible 97 to 99%. Almost nothing goes to waste. It's just elegant.
Okay, so the process we've just walked through, using SMR for the hydrogen and Haber-Bosch to put it all together, that produces what's known as gray ammonia. But as the shipping industry scrambles to decarbonize, it's discovered that if you tweak this recipe, you can create a whole spectrum of different colors of ammonia. And it turns out, not all cargo is created equal.
First up, let's talk about blue ammonia. The production process is exactly the same as the gray ammonia we just learned about. SMR plus Haber-Bosch. There is only one key difference: what you do with that CO2 we mentioned earlier. Instead of just releasing it into the atmosphere, you capture it and store it, usually deep underground.
using a technology called carbon capture and storage, or CCS. This makes a big difference, lowering the emissions, but you're still starting with natural gas. Green ammonia, on the other hand, is a whole different ballgame. This represents a really fundamental shift. With green, we throw out the SMR playbook entirely. Instead of getting hydrogen from natural gas, we get it by splitting water molecules using a process called electrolysis. And here's the most important part. That electrolysis is powered by renewable energy, like wind or solar. The result? A way to make ammonia with very, very low, almost zero carbon emissions.
This table really lays out the whole spectrum of options for us. You've got gray, which is mature technology but has high emissions. There's blue, which cuts those emissions and is commercially available now. Green is the one everyone's excited about, the emerging low-emission champion. And there are even others in development, like turquoise ammonia, and of course, coal-based ammonia, which is an old process with the highest emissions of all.
And all of this brings us right back to those ships at sea. Every single one of these production methods presents a completely different set of trade-offs in cost, in technological maturity, and of course, in environmental impact. For the entire global shipping industry, deciding which of these pathways to invest in is, well, it's about nothing less than charting a course for the future of global trade itself.
So we'll leave you with this final question. The chemistry, the engineering, the processes, those are all pretty clear, but the path forward for the shipping industry, that is anything but. So which color of ammonia will power the next generation of container ships, tankers, and bulk carriers? The answer to that question will have multi-trillion-dollar consequences. Thanks for joining us.